neutrino-nucleus theory. Yeah, for physics beyond the standard model, with a focus of neutrino-nuclear scattering and also dark matter nuclear scattering. Actually, this year is the year of the horse. The horse in Chinese word is 马, exactly is 圆桌马子马. Yeah, use this opportunity. I want to wish everyone here 马到成功, which means may you successful arrive as quickly as a galloping horse. Okay, yeah. Okay, before going to physics, I'd like to thank all my collaborators. Without them, I can't have this talk. Of course, this is not a Zoom call. I hope one day I can bring all my collaborators together, have a Zoom call. Okay, today my talk will mainly include 4 parts. First, I will give a brief introduction about the neutrino-nucleus scattering and dark matter nuclear scattering process. And then I will discuss some recent work on ab initio calculation of elastic neutrino-nuclear scattering process. And then I will talk about inelastic scattering. At last, finally, I will give a short summary. The first part is the existence of dark matter is well established from its gravitational effects on visible matter. For example, these rotational curves of galaxies. From if this is our university, the galaxy is only have visible matter, the prediction is the curve is like this. But the observation gives this curve. It's showing the these stars or gases in the outer side of this galaxy orbit. It is have too fast to hold by the visible matter only. So this is a very good evidence. And also they have gravitational lensing here, and also Bartlett cluster. This is bionic matter. This is shown. It's like dark matter or something. Yeah. And also this is cosmic microwave background. It is a very small inhomogeneous of the temperature. It is corresponding to the matter density. That's showing also is yeah, if we put dark matter, can produce this spherical power expanding using harmonic oscillators. Spherical harmonics, sorry. Yeah, for the theorists, they proposed a lot of dark matter candidates or theories to probe dark matter, the nature of the dark matter, and the mass of the dark matter actually span a terrible region. Yeah, it's I think it's it's like beyond the 30 magnitude, order of magnitude. I also asked ChatGPT to make a similar process like this from these nature people to show neutrino process. Actually, neutrino also is very interesting. That can link to CP violation or Majorana or Dirac particles, and even the absolute mass. We don't know. There are a lot of open questions and rich physics. So my talk will mainly focus on use this dark matter or neutrinos nucleus scattering to probe the nature of the dark matter and the neutrinos. First is inelastic scattering. This is dark matter or neutrino hit the target nucleus, and the nucleus get a recoil, but it remains ground state, not change. In the inelastic scattering case, again, the dark matter or neutrinos hit the target nucleus, and then exactly the nuclear states go to excitation states, and then the nuclear excitation states decay and get some signals can detectable. This, yeah. For the dark matter search from experimenter, they have different ways in collide, indirect. Today, my talk will focus direct detection. It is as shown in this picture. Usually, experimentalists they put some detector in the curve deeper underground, and then waiting the dark matter hit the detector, and then the target nucleus in the detector get a recoil, and then we can get a signal of the dark matter events. Yeah, there are a lot of larger scale experiment all over the world. As showing, for example, here it's the dark matter experiment. And for neutrinos, I'd like first start with the we call the coherent elastic neutrino-nucleus scattering case. This is we simply call the seventh. Seventh is a neutrino interaction with a nucleus where exchange rebirth, and the nucleus recoil as a whole and without excited to go keep without excited to excitation state and keep at ground state. Actually, this seventh is first is proposed from theory around it is around 1874 by Friedman, and after 43 years later, the coherent collaborator first discover the seventh in cesium iodine detector. And then following years, the coherent collaborators did a lot of amazing work that discover the seventh different target nuclei for liquid argon or cesium iodine or germanium. And the seventh also be discovered from the neutrinos in reactors. Here two examples. Very recently, the dark matter direct detection experiment detector also discovered the seventh from, for example, Panda X and also Xenon experiment. This is actually interesting point because the seventh background will become a very terrible background for dark matter direct detection because they can't distinguish the signals from seventh or dark matter. This is a big issue for dark matter direct detection, and also give a good motivation. We really need to more accurately understand the seventh process. And there are also a lot of different experiments focus on the charge current because seventh only is a neutral current, and also for inelastic scattering. I will talk later. Yeah. Besides the seventh, there have different large value neutrino experiment detector, for example, Juno and the Dune hyperkey. That also can be used to probe the neutrino-nucleus scattering and also dark matter search. I will talk the dark matter search in the large value neutrino detector before end my talk. Okay, well, from the theory side, how to compute the cross-section for this scattering, we usually following the following steps. First, we write a high dimension Lagrange. It is uses the quarks and gluons as a degree of freedom, and then we use the multiple expansion to get this electronic currents or hadronic currents. For example, here is exo vector interaction, and then here is the dark matter current can use this spherical harmonics expansion, get different multiples contribution. And the exo vector hadronic current from quark level, we can finally transfer to nuclei level use the hadronic form factors. The form factors can be get from experimental data or lattice QCD calculation. And finally, we can get the currents in nuclei level. It include Klomber and longitudinal or transverse electric transverse or magnetic transverse. And then we use the many-body quantum method to compute the expectation value of these operators in many-body system to get we call the nuclear response or nuclear form factor or nuclear structure factors. And use this nuclear, I call the nuclear response, we can finally get the experiment data event ratio, as shown here. These couplings come from particle physics in this Lagrange, and then this is nuclear response function. And this is dark matter or neutrino flux. Actually, for nuclear many-body theory calculation, we actually compute this operator. I think this it's nine operators. This is different operator. We get this expectation value in many-body wave function, and then we can get nuclear response functions. This is for the elastic case and inelastic case. Usually, this nuclear response function can decompose to the spin-dependent or spin-independent keys. Yeah, for this, before go to the full multiple expansion calculation, I want to briefly discuss about the leading order contribution for this nuclear response function. First, first is the spin-independent keys. The leading order operator really is this Coulomb response. It is here I show is M operator. Actually, this operator is this form. It is a Fourier transformation of proton or neutron densities, and this is dominant nuclear response function. Usually in particle physics community or dark matter direct detection community, they assume this form factor is to be equal for proton and neutron, but we know it is actually not the case because the neutron density distribution is different from proton density distribution. This will bring a large uncertainty for the seventh or dark matter direct detection. And my work also is aimed to reduce this uncertainty from better understand the neutron density distribution. Mainly, we can use neutron scale thickness to reduce this uncertainty. I will discuss this later. And for spin-dependent keys, it is if we use this Q, it is a momentum transfer Q. If go to 0, we can see this operator it's going to actually it's sigma, it's spin values. So it is actually it's leading order contribution is the spin expectation values. That's why usually for dark matter direct detection experiment, they only need the spin expectation value from nuclear physics community. then get the exclusion plots or sensitive plots for dark matter director detection. Yeah. And yeah, this here show example is phenomenological Hammond factor. It is usually used for spin-independent keys for dark matter direct detection or seventh. It is assumed the density is uniform density with a radial R0 and a Gauss proportion with this surface thickness S. This is Hammond-Funke factor form. So I wanted to use ab initio calculations to refine this Hammond-Funke factor, and then they can be easily used for seventh or dark matter direct detection experiment. For inelastic scattering, this is one example. Is showing the leading order contribution is come from we call the Gumpf-Tyler strings sigma tau. Actually, for neutral current, this is tau zero, no change proton to neutron or neutron to proton. This is from some shell model calculation from this paper showing really this Gumpf-Tyler. This first order Gumpf-Tyler contribution is really dominant compared to multiple expansion and with Coulomb and transverse electric and transverse magnetic and longitudinal multiples. Yeah, we want to compute this nuclear response from ab initio calculation. However, as we know, there have a lot of issues in nuclear physics. We face two significant issues. First, it comes from nuclear force because the QCD is become highly non-perturbative at the low energy scale related to nuclear physics. So we really don't know what is nuclear force. Another big issue is come from many-body problem. Because our system is really need to solve many-body shear equation that can ranging from 2 to even lead to 8. It is and even up to infinite number of strongly interacting particles. This is really challenging. For nuclear force, good see is we have effective field theory, especially chiral effective field theory that and give us a powerful scheme to systematically construct the nuclear force and consistent electroweak currents. For example, here shows, I think most of you already know this is chiral and 3LO interactions. There is from this Fermi diagram we can see two nuclei in and interaction or exchange, pi exchange and out. But here is have some unknown low energy constant. It is include the unsolved short range physics. Here we can expand this nuclear potential as expected importance. We call the power counting and order expansion. Finally, we need to determine or constrain the low energy constant from the experimental data or even once we constrain the low energy constants, we can get a nuclear force. We can construct, we can have many-body Hamiltonian, and then this Hamiltonian can be applied to all the nuclear system, from light nuclear to heavy nuclear, and even to infinite nuclear matter without change any parameter or brand new parameters. Yeah, once we have interaction, as I talk here, is we have we can use chiral effective field theory to get interaction. We can use some many-body method. It is kind of usually we there are a lot of different many-body methods can solve the many-body shear equation. All these many-body method actually it is have a controlled approximation and also can systematically improve. Today, my talk will mainly focus on immediate similarity renormalization group method. This is use a continuous unitary transformation to drive the Hamiltonian go to band or diagonal form and then solve the many-body problem. This figure showing the ab initio process over the past decades. We can see it's 4 years ago. We first time computed the leader 208. I use several different many-body method, many-body perturbation theory, couple cluster, and immediate SRG method. And yeah, but today my talk is focused on the neutrino or dark matter scatter case. It is along this region, this medium mass region or lighter mass region in the well bound this gray region, so it can be computed by ab initio method. So first go to the elastic neutrino-nucleus or dark matter nucleus scattering. As I just mentioned, the dominant contribution comes from M operator. It is nuclear density Fourier transformation for nuclear density distribution. Our idea is we can use ab initio calculation to refine these phenomenological form factors to better understand the neutron density distribution. This is the Hammond form factor density form, and we can get this radial from this density. This for proton case, we can know it from an experimental measurement. But for neutron case, we think this can, if we put the neutron thickness into this radius, we can get the R is neutron radius. And if we get a neutron radius, we can get this R0. We get R0, we can get phenomenological Hammond form factor. We can refine the Hammond form factor. In a word, we can compute a neutron thickness. Here show example is neutron thickness. This is this three is come from ab initio calculation compared to shear model calculation. We can see for ab initio calculation really can do the reproduce can get a consistent value for neutron thickness. It is accurate, and then we can use this neutron thickness plus proton charge radial get refined this R0, and then we can get refined the Hammond form factor for dark matter direct detection. Yeah, this give just one example. This is for the multiple expansion factor result. It is M operator and also phi operator. It is we use give one example. It's cesium iodide calculated by valence space immediate SRG method. We get this result. This always come from one. Just I shift it to get for iodide. Yeah, we did a lot of different target nuclei. This figure too dense. Yeah, sorry about it. But we can see for neutron thickness, use different interaction, chiral interaction, and different ab initio method self-consistent Green function. And also this is valence space immediate SRG. It is really consistent compared to a shear model result, really far from ab initio result. We can use this neutron thickness plus this charge radial. It is well measured by experiment. We can get refined Hammond form factor. This is for spin dependent case. Oh no, this is spin independent case. For seventh, this is all the 4 calculations from the 4 multiple operators. Finally, we we use neutron thickness and also this four expectation without multiple result. We can fit in the operator for Hammond form factor R0 and also this surface thickness. Yes.
I was wondering, since you do a very sophisticated calculation, but then you use a very simple Helm form factor.
Yes.
Why can't you just do the full density profile and not use the Gaussian form?
Yeah, good question. Yeah, because I think particle physics community they use this Hammond form factor. If I give them for this expansion value, it is for them difficult to use.
Okay.
Just for simple use. Yeah. But we can finally get these uncertainties. This can cover this our full result. Also, it's this band show have an uncertainty. We can fit in this operator, cover this uncertainty region, and give a simple formula for them to use it. They need to change anything in their code. Just use it. Yeah.
Bai-Shan, I agree with Dean. It is very important to educate atomic and high energy community, not to use Mickey Mouse models. I use her model a lot myself, but nowadays it's not that difficult to do a Fourier transform of nuclear density with all those nucleonic corrections.
Yeah, I can see how to better predict our result. Yeah.
Can I also quickly ask, the nuclei you calculated, are these the detector materials?
Yes.
Okay.
Yes. So, yeah, light nucleus, liquid argon, cesium, iodine, germanium.
So they use a lot of different.
Because this is a target for a lot of experiment. Experiments, different experiments have different detector. Yeah, we can see here is you see this for proton. This is a proton. It's really different from the form factor, different from neutron. This is I want to point out. It's really from ab initio calculus. We find that proton nuclear response is really different from neutron response. This is I think for particle physics community really they can use more accurate result. Yeah, I can consider how to better share our this four calculation result. This four calculation also is actually not only include this density distribution, Fourier transformation of density distribution. This also have a spin orbit correction, and also this is a hydronetic current form factors. It's come from chiral EFT expansion. It's not only for this FM operator, but also include a lot of different corrections. Yeah, this is just to give one example for seventh. Use cesium iodine. This is the first discover seventh from experiment. We use this is refined Hammond, and this is full calculation from valence space immediate SRT method. It's because we refined it fit the four immediate SRT result, so it reproduce them. Of course, this is. Klein history, the form factor is I take from this coherent collaborator. They use phenomenological Klein history, the form factor to describe a theory, theory predictions. It is really far from the ab initio result. Just to give one example, how this form factor affect find this event pictures. Yeah. For Klein history, the form factor, the really large uncertainty comes from neutron thickness. It's around 5% uncertainty from nuclear physics. Yeah, this is go to spin-dependent case. As I discussed previously, it's if momentum transfer go to 0, it is just spin expectation values. We can compute this different target nuclei yeah, for different experiments compared to this shell model, and this is first three is ab initio result using three different commonly used chiral effective field theory, chiral nuclear force. Okay, it's yeah, very real, and in some cases have a larger uncertainty compared to shell model, but most cases the uncertainty already smaller than shell model calculation. This is again I show for ab initio calculation. It's different operators. And also include here we call the two-body currents from electroweak two-body currents. It's I'm not sure. Yeah, this band mainly comes from the different how to treat the two-body currents because we use one body normal order approximation that bring operator density that have a large uncertainty. Yeah, this give one example for dark matter direct detection experiment. For this, we call the LZ experiment. Right now, the LZ in US, located in South Dakota. It is the most sensitive experiment all around the world. Then, this 4 years ago, they give this exclusion plotter. This part or is excluded for parameters, and then they use this published nuclear structure form factor or response functions put a band because we have a larger uncertainty in here. They put this uncertainty into their final result. We can see this band come from our nuclear structure form factors. The final result show it's really also is very large uncertainty region. Yeah.
So do you have a sense about the other band, like the other uncertainties from the
What?
experiment? No, just for the LZ experiment. They should have the band as well, right? From the experiment.
Okay.
No?
Yeah, I don't know experiment.
So the gray band is from theory, right? It's from your theory.
Yeah, agree about that. And this solid one is just for experiment.
Just one curve.
Yeah, I think they just give us the best one, lowest exclusion one, not showing uncertainty here. Yeah, for experiment, they just give lowest exclusion point.
So now you're saying that it's actually okay.
But this band is come from nuclear response functions. Really, it's large uncertainty. Yeah, you see from LZ, it's if before it's LUX, the next generation is LZ. They just improve this region, but the nuclear response function uncertain, right? same magnitude or the magnitude. Okay, let's move to inelastic scattering. Yeah, first is for neutrino-nucleus scattering. Really is I'm targeted for dome physics. Dome is I think largest experimental facility in the world. Yeah, but the dome detector will detect the neutrinos from being or supernova, cover all the energy transformation region. So I'm interested in its low energy region. But low energy region, we can see this is from a different RPA or shell model or other. This is Gamma of Fermi beta decay experimental data, but use some phenomenological framework to compute the cross section. It really have a large uncertainty for this cross section. It's several order of magnitude. So it's really large uncertainty. So for dome, it is can become a really large background for their discover the neutrino nature of the neutrino, and yeah, in dome there is they want 10% less uncertainty. This required the charge current neutrino-nucleus scattering cross-section be known about 5% uncertainty. So for inelastic scattering, first leading all the contribution come from Gamma-Taylor transition, but the Gamma-Taylor transition actually similar from we can get the insights from M1 transitions. M1 transition we have experimental data as showing the blue one. It's a liquid argon 40 nuclei, and this is show it's a shell model calculation. Really, this is when shell model calculation use Bayer operators. This operator they really overestimate the experimental data. We know shell model you really need to put some quantity factor or effective operators to reproduce experiment data. So after put some quantity factor or fit this experiment BM1 that can have some factor, put this factor into the wave function that can compute the sigma tau, these sigma tau operators. And then this is a Bayer operator. If put a quantity factor, they get this cross-section from shell model calculation. You can see really it's a large change. So this means also for phenomenological shell model calculation also can have a large uncertainty. We use ab initio calculation, just use Bayer force and then compute the cross-section. We find our result really this I use two different commonly used chiral interaction. We can see this is red and blue. It's ab initio result compared to large scale shell model using quantity factor. It's really consistent. Yeah. But this is only for Gamma-Taylor, means from ground state to 1+ state. However, there have a lot of multiple operators. After consider all the multiple multiple up to 4+ or 4-, we finally get the result from ab initio calculation. The cross-section is like this. Compared to Gamma-Taylor only result, it's this one. It is really can get very different result. Recently, we put this ab initio calculation for neutron current case. Here is up to, I think, neutron separation energy threshold. Use ab initio result. Above that threshold, we combine the continuous RPA calculation for giant resonance region. We get this picture. To better understand the cross-section for inelastic neutrino-nucleus scattering case. For charge current, I'm working. Here show example. It's use Mali or something. They use low energy region. They can use this experimental data, Gamma-Taylor transitions or film transitions to get quantity factor or refine the result. But above this this low energy region, like only QRPA or CRPA available. This also give a good motivation. I'm working on use ab initio method to compute this giant resonance region. For inelastic matter nucleus scattering case, it's first it's why we are interested in inelastic dark matter nucleus scattering, because here is showing example. It's for inelastic scattering, the cross section is very small compared to elastic scattering, so that can be smaller. But for background, for elastic, it have a smaller background compared to elastic secondary. Here background mainly come from neutrino-nucleus secondary. Here we can, for example, this picture just for showing. For example, this is elastic secondary because they can get nuclear ratio in MeV level. This region, the background really is small. Finally, we can get benefits from inelastic secondary, even their cross section is it's smaller than elastic secondary piece. Here show is one example. It's one model called the dark photon models. They use this coherent or seventh experiment detector to use these dark photon models and get these sensitive plots for elastic secondary. This is the most limit for different detectors. They have some empty space to be probe. We use elastic secondary. This is a dark photon model. Here is from the limits from the elastic secondary, as shown in previous slides. We use the elastic secondary. We find this is use three diff in the SBNT. It's a short baseline neutrino detector in beam libel. We find really elastic case can give more sensitive plot, sensitive compared to elastic keys. This is another model we call the. Oh, I should change this. This is just type. This is the dark photon model. This is the electronic dark matter model. Being show result. This is we use ab initio calculation for nuclear structure from factors, get these sensitive plots or exclusive plots. Okay, give a short summary. Right now we can use ab initio method to compute the nuclear response function for dark matter or neutrino-nucleus secondary process, include light nuclear to medium mass or heavy like xenon or cesium iodine target nuclear. And the cleanly older contributions is neutron thickness and spin expectation value, and also gamma-Tyler transitions. So I also want to point out it's inelastic secondary channel really is I like it. This, however, this channel not probed much previous. I really want to draw attention to pay this inelastic secondary channel. Yeah, for because it offers additional channel for dark matter detectors. In a word, ab initio method can reduce nuclear physics uncertainty in search for beyond the standard model physics, enable more robust interpretation of current precision experiments. Okay, thank you.
Are there any questions in the audience? Are there?
A nice talk. So I have a question. When you showed, for the low line strength, you use the ab initio calculation and use this continuum QRPA for the resonance region. Is the continuum QRPA based on chiral interactions, or it's just something else used to estimate the contribution?
Yes, yeah. Right now it's because right now I'm trying to use the ab initio method to compute this giant resonance region, but it's yeah, because I use valence space in media SRG framework. It is need to change the method to compute the giant resonance region physics.
So still working. Estimate like how large this contribution should be in the cross section, right?
Yeah, but I can't estimate the result from ab initio, how the CRPA result or accurate or how uncertain come from the CRPA. I don't know. Hopefully in the future we can get some insights from ab initio calculations.
And a second quick question is these inelastic neutrino reactions, they are like really important in when you consider like exploding stars, you know, supernova, core collapse supernova, they like help to revive the shock. And so my question is, I guess, you know, could you provide these calculations for astrophysical interest? And there you would have to do the finite temperature calculations, right? Because the nucleus is really excited and so on. So these then would be finite temperature IMSRG calculation. And I know this is something Heiko has been doing. So are you?
Yeah, that is interesting. Yeah, I'm also interested in flight temperature immediate such framework, but I no idea how to do this neutrino or solar neutrino. Yeah, but good to discuss with Heiko.
Okay, thank you.
Very impressive results. Thank you for sharing. So I had a question about the failure of the large scale shell model calculations, why they're so far off. That's kind of surprising. And do you understand why that is and why it's not also affecting the ab initio calculation? Because in some sense, you would think there shouldn't be such a huge difference between the two.
I don't know. I think actually, yeah, for shell model, I don't know.
Neutron scheme, right? So then in shell model, it's mainly if the valence particle is mainly about neutrons, the protons are almost do nothing about the radius for the rest of the neutrons. So then
You're saying because the protons are frozen that they're not really
yeah. So if
taking into account.
if you take the full configuration, the protons will interact with the outer layer of the neutrons.
Yeah, I think for shell model calculation, I use this form factor, weak form factor, get the weak form factor, and then use the weak form factor, get the neutron radius. Yeah, this is just a derivative of the form factor. But this form factor use Bayer operator, not put effective operators. I think here will bring some uncertainty. Shell model.
I was just going to make one more comment with respect to the Helm form factor from what Dean and Vitek were saying. I was just checking that extraction, like that way of extracting densities was made 70 years ago. And it is because we didn't have computers, so we could actually make it analytically.
Yeah.
I really fear that you could be washing out the sensitivity, the decimal places that you're really after by doing that. And one suggestion, which is what I do when I want to convince myself of one or the other, is run the calculation in both ways, like by compressing the information through the Helm form factor and by not doing it, and see if your conclusions change. Because if they do change, then that means that that compression is actually a bad idea. And if they don't change, then that makes me question how much actual ab initio input was needed. If you could have just parameterized this, like if only bulk properties are needed, if I only need a good estimate of the radii for this thing to make sense, that I think will be useful information to have. So I just wanted to share the thought with you.
Yeah, thank you. Yeah, I want to point out another is for seventh really that probe the neutron density distribution. But this really have a large uncertainty for Hammond form factor. I think a previous Hammond form factor mainly is constrain the parameter from experimental data. It's mainly for proton density distribution rather than neutron density distribution.
This is one question. So the uncertainty due to the in the ab initio calculation for different nuclei for dark matter detections are all correlated, right? So the error bars for different nuclei from ab initio they are correlated.
Yeah,
but they all come from the same chiral EFT.
Yes.
Right. And I know people doing dark matter detection, they want to use different nuclei to pinpoint the property of the dark matter. Yeah. So the correlation, I wonder whether correlations, the experiments will be interested in that correlations.
To explore, yeah.
Yeah, because the reason they have these different detectors is because they want to have some handle on those the dark matter.
Okay, yeah, that is a good point. Yeah, I waiting for the separately but target the nuclei, but we can together see that. Good.
Since you're here, can I quickly ask a question? The 18th slide, you
18.
show the three ab initio calculations. Yeah. So here, and I just wanted to make sure these are all within medium SRT, right?
Yes.
So
yes.
technically, if there's any, okay, this only shows the difference between different low energy constants in a way, or like
different
different
interaction, because they also
different
have
interactions.
the delta interaction have delta S.
Oh, okay, like with regulators are different too. So can one do these calculations, any of these nuclei with another ab initio method?
Yeah. Right now, couple class can do this. Use deformed, but without protection, no problem. Yes. And also, I think one example is here. I think I show one is self-consistent grid function.
Okay.
There is here just for xenon case. Yeah, this is I only get published the result from self-consistent grid function compared to valence space immediate as a result. Really consistent for set interaction. If we find this is red, this is pink, it really
Okay.
consistent. Yeah, for neutron slit thickness, many body methods and will describe it.
Okay, excellent. Good. Any other questions? Yeah, please.
So if you imagine that there is this reaction of dark matter with nuclei, will structure factors like change what's the mass of dark matter particle you extract, or maybe like coupling constant, or it doesn't matter?
You mean dark matter change after hit the new nucleus?
Yes. Well, if there is dark matter interacting with the nuclei, you will basically find dark matter, but the question is, do you get any inference on the properties? Like what is the mass, what is the coupling constant, and so on?
That for the inelastic scattering, it's not so sensitive to the details of the nature of dark matter. But for inelastic scattering, very sensitive to different operators. That also very depends on dark matter models. That's why it's not proven much by the community. That case is for inelastic scattering, they're very sensitive to the operator of dark matter models or something. But for elastic case, it's not so sensitive to dark matter. But for dark matter mass, the exclusion plots show as exclusion points as dark matter mass. It is already in there. Yeah, but another is I want to point that it's some there are a lot of models. Some model also think dark matter hit the nucleus. Dark matter also can get excited states. A lot of different models. Yeah.
Another question.
Sure.
Yeah, so at the very beginning, you have this formula where you parameterize your total cross-section. So I was wondering, so you have this part from hadronic structure. So do you expect that hadronic structure doesn't modify it inside nuclei? But what about things like short-range correlations? So basically, right, you can have hadronic form factors and can be different inside nuclei.
Yes, that is, but I think this also can affect, but most because this is hadronic form factors. It is just this QQ quark expectation value in nuclear. You can get form factor. This form factor come from experimental data. Right now I use that. So this will or every effects already included in the form factor. But if you use large QCD calculation, I think yes, high order contribution effects correction will come into the form factors. Yes. Does that make sense? Yeah. Maybe we can talk later.
Anything else? Nice discussion. Don't see anything on Zoom. Okay, let's thank Bai-Shan again. Right now we'll be here the whole weekend.
Yes, yes. I got the 14 or
Yeah, 2114 is where he's sitting.